So today we're going to look at conservation of energy in orbital motion. Remember that gravitational potential energy was mgh when we were near the Earth's surface, but that's only when we could call our gravitational force mg. But now we've got this big old nasty thing for gravitational force. Remember that potential energy was minus the integral of our force. And a lot of times we said dx. In reality, it's dr. Any sort of, it's actually the dot product of f with dr. So you're integrating in the direction of the force. And in this case, the force is in the radial direction. So our gravitational potential is the integral with respect to r, or minus the integral with respect to r, of our gravitational force. I don't think I gave you the minus. The minus just indicates that it's attractive. It's in the negative radial direction toward the center. But that technically is part of the formula. Usually when we're calculating force, we just care about the magnitude. But the negative makes things work out properly for potential energy. So the integral of minus 1 over r squared is 1 over r. And then we've got a negative outside the integral. So we get a negative, and then the g and the masses are constant. So this is the gravitational potential energy of any pair of masses. This is just an exercise to show you that the formulas work out the same when we're near Earth, so using mgh is pretty easy. So if you go from sea level to Everest, my change in potential energy according to the mgh formula would be 84 times 9.8 times 8848. My change in gravitational potential energy would be my final gravitational potential energy, which is minus g times the mass of Earth times the mass of me times my final would be the radius of the Earth, 6370 in kilometers, so 000, plus 8848 minus my initial potential energy, which becomes plus g mass of Earth, mass of me, over the radius of Earth. So this is my change in potential energy using mgh formula. This is my change in potential energy using gm1 m2 over r from sea level to the top of Everest. And if you calculate those out, you'll see they're pretty close, very close to being the same thing. Remember that energy is a scalar, so we can just add up potential energies. So if I want to find, if I've got a mass 2m at the origin, mass 3m there, and mass 5m there, I just add up each pair. So 2m to 3m, I've got 2m times 3m, and those are a distance 5d apart. Then I've got 2m and 5m, those are a distance 12d apart. And then I've got 3m and 5m, and I happen to make this a nice 5, 12, 13. That's a Pythagorean triple, so that's that one. And we can add all those up. Let's see, this is negative 6 over 5 minus, what is this, 10 over 12, which is 5 over 6, minus, what is this, 15 over 13, frac. Okay, that's not a very pretty number, but total potential energy of this configuration is minus 1243 g m squared over 390 d. So you can calculate that out. The work done to assemble the distribution is the exact same thing as the total potential energy. So I think some of the book problems say, how much work do you have to do to assemble this? And that it's a negative amount of work, which makes sense because they tend to come together on their own. Gravitational force is attractive. So in a planetary orbit, think about what forces are acting, what forces are doing work. Well, the only force acting is gravity. So What is true about mechanical energy? It's going to be conserved because the gravitational force is the only one acting in a circular orbit. Gravitational force does no work. On an elliptical orbit, it is doing work, but either way, gravitational force is conservative, so mechanical energy is conserved. So we can say initial mechanical energy equals final mechanical energy, and then, so we can say 1/2 mv0 squared minus g over r0 equals 1/2 mv final squared minus g over r final. We can say that for any given orbit, 2 different points in the Earth's orbit, whatever. When is Earth moving the fastest? Well, we already know that it's moving the fastest at perihelion. We learned that when we were talking about Kepler's second law, but we can also think of that in terms of energy. At perihelion, if you were writing this on a quiz or test, you should use words, not the shorthand that I'm about to, but a smaller r corresponds to, potential energy is proportional to minus 1 over r, so a smaller r corresponds to a lesser potential energy. It's a bigger negative potential energy, so it's a smaller amount of potential energy, and since mechanical energy is conserved, that corresponds to a greater kinetic energy, so that's when it's going the fastest. That's something I should have said initially when we're dealing with potential energy, is watch out for that negative. As you can see, as r goes to infinity, potential energy goes to 0. But because it's 1 over r, you think, oh, well, as r gets bigger, potential energy is getting smaller, but it's becoming a smaller negative, which means potential energy increases. As r increases, potential energy increases, and vice versa. As r decreases, potential energy, or whatever, potential energy decreases. So don't let that negative fool you. It can be tricky because it's a negative 1 over r. So comet has speed v when it's a distance r from a star of mass m. What is its speed when it's a distance r over 2 from the star? Well, we can apply conservation of energy, 1/2 mass v squared minus g m over r, and we want to know what is its speed when it is a distance r over 2 away. And we can calculate that in terms of the given quantities. Mass cancels out, the little mass of the comet. And we can put this together. So multiply through by 2 because we want to get rid of this. So then we have v squared minus, this becomes a 2 gm over r. This becomes, well, r over 2. The 2 flips to the numerator. So then you multiply by 2 again. It becomes 4. So we got negative 2 plus 4 plus 2 gm over r is equal to v final squared. So we square root it, and so that is the speed when it is a distance r over 2 from the star. Find the total mechanical energy of an object of mass m in a circular orbit of radius r. For this, I'm going to flip back. Rather than re-deriving, I'm going to go back to when we derived this when we were talking about Kepler's laws, that the velocity for a circular orbit is equal to root gm over r. So I'm going to use that. So the total mechanical energy of an object in a circular orbit of radius r is going to be 1/2 m v squared minus g mm over r. But v is root gm over r, so that's 1/2 m, and it's squared, so that becomes times gm over r minus gm m over r. So we have 1/2 minus 1, so our total mechanical energy is minus gm m over 2r. I put a star by this one because this is one of those formulas that is useful, number one, to know how to derive it, because that might show up on the exam, but also to have in your calculator to have on hand, because it might come in handy for answering a question on the AP exam. All right, just continuing on, going to keep chugging away here. Satellite of mass m is orbiting a planet, initially in a circular orbit. How much work must be done to move it into a circular orbit of radius 3r? This is the kind of question where knowing this formula is useful. So you might, if you didn't think about this total mechanical energy, how much work must be done, you might just think, oh, well, it's changing its potential energy, find the change in potential energy, that's the work. But to be put into a circular orbit, you also need to be changing the speed of the object, so you have to be careful about that. So we know work is equal to change in mechanical energy. So to put it into an orbit of radius 3r, we need to take the final mechanical energy, and we just derived an expression for total mechanical energy. So our final mechanical energy is going to be minus g mm over 2 times 3r minus, so it becomes plus, our initial mechanical energy, g mm over 2r. So we have minus a sixth plus a half. And my brain is hurting. I think that's a third. Yeah. So that's equal to positive g mm over 3r. Just applying conservation of energy. A bullet of mass m is fired upward from the surface of a planet of mass big M and radius r. What minimum speed must it have to escape the planet's gravity? Well, escape means we go out to infinity. So practically speaking, you can never escape a planet's gravitational pull because it's always some distance r away that's not infinity. But this is calculating what's called escape speed. So escape speed, we need to make it out to infinity, which means that our final, we just barely make it, so at infinity it has 0 speed, and at infinity potential energy is 0. So basically what that means is that the total mechanical energy is 0. So 1/2 mv0 squared minus g mm over r is equal to 0. And we solve, this is called escape velocity, so I write VESC equals, we add this to the other side, that's gm over r times 2 square root, and this is what is known as escape velocity. And I put a star by this again because this is something that pops up on the AP exam, useful to know, good to know where it comes from. Couple interesting things related to gravity, black holes, and tides. You can read about them in your book. I'll talk to you about them a little bit when I return. And then you have homework. So just like with non-gravitational things, we can apply conservation of energy to planetary orbits because the gravitational force is the only force acting. So mechanical energy is conserved. We can use it. And it shows up a lot on the AP exam.